Hello everyone, my name is Evi Palato from geoengineer.org. I am pleased to introduce you to October's 2015 online lecture organized by the International Society for Soil Mechanics and Geotechnical Engineering. This month, Professor Gazzetas will be talking about soil dynamics and seismic geotechnical engineering. George Gazzetas is a professor of soil mechanics at the Department of Civil Engineering, National Technical University of Athens, Greece. He obtained his 3 degrees at National Technical University of Athens and MIT. His research and teaching has covered a wide range of topics in the fields of geotechnical earthquake engineering, soil mechanics and foundations, and he has over 400 research publications in journals and conference proceedings. Also, he has received 13 international awards for his research. Note that after the completion of the webinar, Professor Gazzetas will be happy to answer any questions posted on the ISSMG question and answer platform. The platform will remain active for 2 days. It is located below the present video and you may access it with your GeoWord account. Enjoy the lecture.
Good morning, dear audience. Today my presentation will be on soil dynamics and seismic geotechnical engineering. Right away, the main contents of the presentation refer to soil amplification, soil foundation structure interaction, and dynamics of sliding systems like slopes and walls. My name is George Gazzetas from the National Technical University of Athens in Greece. Now, one of the topics that I will not cover is liquefaction, a very important topic of soil dynamics, but for which the earlier presentations of Professor Tawata and Professor Kubrinovsky, they have covered it very well. So there is no point for me to cover that material as well. Now, some typical applications of soil dynamics. Machine foundations, the oldest, perhaps, or one of the oldest uses of soil dynamics or applications of soil dynamics. Geotechnical earthquake engineering, the topic of my presentation, but many other applications like foundations of open sea structures, blasting, traffic, rail-induced vibrations, and so on, are part of soil dynamics, but geotechnical earthquake engineering is by far the most significant one. An overview of geotechnical earthquake engineering shows that it comprises engineering seismology and seismotectonics, a very important part which touches the specialty of seismology, seismic soil amplification and liquefaction, as I mentioned, which we will not cover, dynamic soil foundation structure interaction, and of course earthquake response of numerous purely geotechnical or less geotechnical or partially geotechnical structures like earthfill dams, embankments, retaining walls, slopes, tunnels, and so on. Now, soil dynamics is based on 3 sciences, if you want to call it that way. Wave propagation, which is basically the dynamics of continuous systems, like soil is, dynamics, or what has become known as structural dynamics, because eventually it is our structures on top that will interact with the soil, and it is their behavior that is of our interest, and of course, soil mechanics. Now, let us go directly to a very crude sketch, very, attempt to be an artistic sketch, which shows a fault where the earthquakes originate, and these faults slide or rupture when the stresses induced by the continuous deformation of the earth accumulate, and the shear strength on these lines is exceeded. When this happens, waves are emitted anytime this rupture moves along the fault. And it is not only a plane, it is a whole surface, as you can see here. What happens every time there is a little rupture is that waves are emitted and sent everywhere in space, in the ground. Eventually, all those waves from these various subsources, if you want, they arrive at the site, they combine naturally, and they give what we feel as the shaking of the ground. The ground motions, as it has become known, but I really prefer the term ground shaking or ground vibration. Like this point experiences this type of vibration, usually expressed in terms of acceleration as a function of time. Now, once in a while, the faults rupture all the way to the surface, or as we say, the fault emerges on the surface. And of course, this creates additional problems beyond the point, beyond the problems of ground shaking. Now, just to say a few words on the magnitude. Now, there has been a lot of magnitudes over the years. I think most people are familiar with the Richter magnitude. We may not know how it is computed, but it is computed basically from the amplitude of displacements at very large distances. It is a very old but very popular way of measuring the strength, the energy of the earthquake. But these days, seismologists prefer what they call moment magnitude, which derives from the so-called seismic moment of the earthquake. And the seismic moment is nothing else but the shear modulus times the area that is rupturing during an earthquake times the average displacement. And since this is a huge number, the shear modulus is the modulus of rock. The area is very large, as we'll see in a second. The displacement can also be very large, the average displacement of the order of meters. This is a huge number. It's not convenient to use it. They found out that if they multiply the logarithm of that number by 2/3 and they subtract this number, the value of MW is not all that different from the magnitude that was familiar for so long. The Richter magnitude or the surface wave magnitude or whatever else it's called. Now, it turns out that the magnitude is almost a unique function of the length of the rupture, how long the rupture will be. And what I have down here, before I go to the diagram, is a sketch, a very, very, very crude, typical sketch with the dimensions of a fault. The ground surface is supposed to be here, and a magnitude 7 fault will mean a fault that ruptures all the way down to the brittle part of the crust, which is not more than 15 to 20 kilometers. Most fault ruptures are here, with the exceptions of faults in the boundaries between plates, where the fault movement is a movement downward. It is a subduction zone type of earthquake, which earthquakes can be very deep, as we'll see in a while. But the usual earthquakes that disturb the people and are of engineering interest are 15 to 20 kilometers, and a 7 magnitude mean 50 kilometers length. A 6 magnitude may be a rupture somewhat like this, 10 to 12 kilometers. A 5 magnitude, much less, 2 to 4 kilometers only. And this diagram, which is a purely empirical diagram, so gives the magnitude, the moment magnitude, this particular magnitude, as a function of the surface length. And you can see that a 10 kilometer surface rupture might mean a 6 or 6 something magnitude. An 8 magnitude earthquake might mean several hundred kilometers, 400 or 500 kilometers length. A 9 magnitude event like the one that took place in Japan 4 years ago, 12/11, may mean close to a kilometer long fault. So that's the idea about what is the source of this earthquake. Now we go back to see what are the consequences of these ruptures on the surface. First, starting with the ground shaking, the accelerogram that are recorded on our accelegraph stations. And I have here a tremendous variety, just arbitrarily chosen, of earthquakes from here and there. Ground motions, you see here different amplitude, common amplitude in all of them, different amplitude, different intensity of motion, different duration, and of course different details of the motion, or frequency characteristics, as we like to call them. And these frequency characteristics are usually represented by engineers with the response spectra of these motions. Now, seismologists prefer the Fourier spectra, and I think we now understand what is a Fourier spectrum, but the response spectrum is of more practical use to civil engineers. Now, a response spectrum of a particular ground motion, of one of the motions that you saw before, could be in principle understood or obtained as if we had a rigid, huge table, on which table we had a number of oscillators. Each oscillator has a fundamental natural period, which is square root of m over k times 2 pi. So each oscillator, because of the larger length of this bar, which means larger length means smaller k or larger period, each of these oscillators has a period which corresponds down here to this diagram. Now, if we subject this plate with this particular motion, the particular time history, these various oscillators will respond quite differently. Very differently. In frequency characteristics, in amplitudes, if we only take the maximum values of each acceleration and plot them here versus each frequency, then we construct the nearly elastic response spectrum. It's not truly elastic because we have a little bit of damping usually on this. Typically we present this spectra with 5% damping, but it is in essence a linear elastic spectrum. For example, this particular oscillator with this period experienced this maximum value of acceleration. We plot it here horizontally. So this is the spectrum. Now, if you want to see the response spectra of all the recorded motions that I showed you before, the arbitrary shape, you can see here that this spectra can reach very large values, 2g accelerations, dropping down a very wide period range. And I have here a typical design spectrum which the codes, this particular case Eurocode 8, the European code, but more or less all the codes are similar, which would have given something like this. So that's the ground shaking. Let's go to finish with what are the consequences of the surface fault rupture when this fault appears on the surface. What's happening, how our structures behave, and let's see a few examples. I have taken the example from the Chichi earthquake in Taiwan. The Chichi earthquake was a very strong earthquake, 7.5 or so magnitude. But what is peculiar is that the fault, a very substantial fault, that not only reached the surface, but gave huge displacements, you will see in a while. First of all, it's anything but a straight line. Evidence that reality sometimes is much more complicated than a simple nice plane that we draw. Now, in this particular case, this was a thrust fault, meaning a fault produced by compressional tectonic forces. And because of this compression, this right-hand side part of the ground moved upward. How much? 7 to 10 meters in this particular location. Smaller heights, smaller offsets in other locations, but in this particular case, let's see what is happening here and there. But notice, it is very important, how unpredictable the location of this fault was. They did not know it ahead of the earthquake. Yet, this earthquake, first of all, because of the upward movement here, created these faults, 6 meters, and of course, the abutments of this bridge moved upward, and this bridge, being a simply supported bridge, could not escape the fall of the decks. But let's go to see what is happening on the other side. On the other side, the dam. Yes, the dam also was broken. This concrete dam, not a very large, not a very major dam in height, ruptured. This distance here, this differential height, is 9.5 meters. But it was a fortuitous event that this part moved upward rather than downward. And upward means that the lake was contained. The water escaped through the broken spillway, which is what it was here. You can see here the gates of the spillway. Okay. But there was no other disaster. But let's see other cases. In China, 2008, there was the Wenchuan earthquake, also a large magnitude event with many victims. The important thing is the rupture also appeared to the surface. Not so large displacements, not so large offset, as we call it, but 2 to 5 meters is enough to dislodge this part of the bridge, the decks of the bridge here. But there have been also successes next to the fault, and it is very important for civil engineering, for geotechnical and civil engineering, that even a 2.5 meters rupture very close to a school did not damage it at all. This school is intact, 2.5 meters displacement. It was in the upper part of the fault, the moving part of the fault, okay, the hanging wall, as it is often called, only 2 meters away, but no damage at all. Contrary to what happened to the other buildings, we don't know whether they ruptured because of the fault appearing on the surface or the shaking. But the most interesting and significant interaction, if you want to call it, between a rupturing fault and the structure is this one from Turkey, from the Izmit or Kocaeli, as it is called, earthquake, where this very well constructed village building, well, what happened here? Well, it underwent a 2.5 or 2.5 meters fault rupture appearing on the surface. But this fault made a turn around the building. It was deviated. It moved because of the presence of the building. The building fell down 2.3 meters, but this failure is a very slow failure, and there was not a single crack on the building. We found out that this building, because of the soft, or thanks to the soft soil, it had extremely good foundations, built by the villagers themselves, not by engineers, but very strong box-type foundations, as you can see here, and they survived intact. They forced the fall to go the easiest path, not really to cross the strong building. So, after all these successfully and non-successful events, we have understood that we can possibly design structures, not on purpose, but just in case a fault ruptures underneath. And here is an example of a typical numerical analysis of a tall building, 5-story building, but on very strong box or mud foundation, which in this particular case undergoes a very significant 3 meters dislocation at the ground, at the base, and manages to almost escape from this. Of course, it suffers a significant rotation, but if you can see the columns and beams, there isn't much distortion in the structure itself. It would have survived even if not intact during the earthquake. So that's the story with the fault rupture. We believe that the engineering profession is in a position to design for at least a hypothetical fault rupture underneath. Of course, we're not crazy to go and put a building directly on a well-known fault, but usually faults that rupture during earthquakes are not so well known. So let's proceed with the most important part of my presentation, which is how we handle the seismic shaking, the ground motions. And I have here this, again, this overly simplified and out of scale sketch of a source, which may be of the order of tens of kilometers in this distance, more than tens of kilometers in the other direction, and the waves emitted every time a part of the fault ruptures or slides one part over the other, and those waves eventually arrive in the location of our interest, the structure and the soil through which the waves propagate. This propagation through soil is what gives the term soil amplification. I have it here in a different sketch, similar sketch, the fault rupture, to show that there is a plane rather than a single line. The waves emitted produce motions within a very short distance, like even a neighborhood of a city or a small village or a town, which motions are three different points with different thickness or properties of the soil, may experience quite different motions, different in amplitude, peak values, A of A, P of C, but also different, as you can see, periods of oscillation at these points. And this we usually express again through the response spectra, which then show that the peaks, not only the peak values of acceleration, but also the peak values of the spectral accelerations, the accelerations that a structure will experience, differ in terms of the period where these peaks occur. So this is, in broad terms, soil amplification. It is produced by the propagation of seismic waves through the soil. Now, here is how it is produced. A very simple picture shows that the waves propagate vertically upward, and as they enter the soil stratum, they produce simple shear in the soil. Now, is this vertical shear wave and horizontal ground a good assumption? A very reasonable, simple way of seeing the earthquake. Yes, the earthquake, it is predominantly shear waves. Why? Because the source is a shear failure, is a shear rupture. So it is predominantly shear waves that emanate from the source. And then do they arrive vertically or under a slope, under an inclination, under an angle? Well, there is the so-called Snell's law of refraction. You may remember it from acoustics or your high school physics, that as the wave progressively moves under a certain angle, it hits interfaces where a weaker layer is on top, it becomes more and more closer to the vertical. So this idea of vertical shear waves producing simple shear motion in the soil and eventually giving an amplified motion at the top is what is really the soil amplification. Now, if we want to model this in the laboratory, we have to impose purely shear waves. This we'll usually do with torsion in the laboratory or with simple shear devices, and we study the behavior of cyclic shear stress versus the resulting shear strain, and we eventually construct loops like this. Loops which mean energy loss during a complete cycle of motion. Now, upon loading and unloading and reloading, the soil follows this particular path from here to here and to here. We understand that the shear modulus at small strains what we might call the elastic shear modulus, or Gmax as we call it in soil mechanics, is not really representative of this complete cycle. What is more representative is this sort of average shear modulus. Not the maximum nor the minimum, something like the minimum, the average. It's the one which is the slope of the line which connects the center, the zero, with the tip of this loading and unloading curve. So with this average shear modulus, we do linear analysis. We like linearity because it's much easier to do it, especially in the old times where analytical solutions were the rule of the game. But even today, we prefer analysis with linear modulus than with the complete nonlinear stress strain loops. But it's a pity not to account for this energy loss. Well, we do account for this. This energy loss is accounted for through this damping ratio. Now, they call it critical damping ratio, but this is a totally terrible. There's nothing critical about this damping ratio. Is the hysteretic damping ratio. We'll see how the word hysteretic arrives from, where it comes from. But the damping ratio associated with this complete circle is proportional to the area of the circle and inversely proportional to the elastic energy, which is nothing else but this area here, the elastic energy, and divided by 4 pi. So with this damping ratio and this active modulus and or effective modulus or mean modulus, this is then how we reproduce the behavior of the soil element which undergoes the simple shear during the vertically propagating waves. At small amplitudes of deformation, like you see here on the top, small shear stress, the shear strain is also small, and it is probably a more or less linear behavior. The modulus is more or less the same as the tangent and at the origin shear modulus, the maximum shear modulus, and very, very little damping. Theoretically zero damping, but there is always a little bit of damping for other reasons as well, which is not part of my discussion. As we keep increasing the shear stress, first of all, the slope of this line, the shear modulus, decreases. There it is here. It has become something like 80 or 90% of the maximum modulus, but also the damping ratio, you see here an area of the loop increases a little bit, and so on. Eventually, when we reach very large amplitudes, the shear modulus have decreased a lot. It has become only, 10% of the maximum modulus, but the damping ratio at the same time, which is plotted here to the right, has increased. So this is the very popular G versus gamma, X versus gamma curve, which allow us to do an equivalent linear analysis to model the truly nonlinear soil behavior. Of fundamental help and importance in soil dynamics. And the interesting thing is that these curves, G versus gamma, and I'm sorry, I changed the symbol, and Xi or beta, or whatever else it's called here, damping ratio versus gamma, are almost unique functions, do not depend on many other things, for example for clays, other than the plasticity index. Very nice, a very easy thing to measure, not many other things, not over consolidation ratio or the nature of the soil. Plasticity index is the one which controls the G gamma and beta gamma curves. Very significant, meaning once we have G max measured in the field, for example, through shear wave velocity measurements, we can have the G versus gamma knowing the plasticity index of the soil. Now, let's go back to see some case histories which will verify that this idea of vertical shear waves and the amplification that is produced, which is the ratio of displacements or accelerations at top versus the base, I'm repeating here, A and C are these 2 points. As the waves go up and down here, they eventually produce a motion at the top which is much higher than the motion of the base. The ratio of these two coefficients is above 1 usually, and at certain frequencies, apologize for this misplaced finger a little bit, at frequency f1, which depends on the shear wave velocity of the soil, square root of shear modulus over the density, and the height of the soil, at this frequency we have a very large increase of motion at the top, and amplification, a resonance phenomenon, and of course, since this value here has nothing to do with excitation, depends only on the characteristics of the soil deposit itself, its shear wave velocity and its thickness. This is called a natural frequency, the fundamental natural frequency of the soil deposit. At this fundamental natural frequency, the maximum value of this ratio, which is called amplification, is 2 divided by P times the damping ratio, which means for a damping ratio of 5%, this gives a value of 12.5 or 12.6 something. Now the second natural frequency is 3 times larger or 5 times larger, the third, but the peak values have become 1/3 and 1/5 of the value here for the same damping ratio. So this is the fundamental, simplest possible theory, and we'll see how this theory has been verified by a most significant earthquake event. The earthquake event is none other than the destruction of part of the Mexico City, the capital of Mexico, during the Michoacan, as it is called, from the name of the area here in Mexico, which produced a huge earthquake in the subduction trends, where it means this part of the ocean moves underneath that part. It created a large magnitude, 8+ magnitude earthquake, and it produced a huge destruction here. Let's see it in more detail. For example, here is a very artistic, so to speak, picture, of course completely out of scale, nearly 400 kilometers away from the source of the earthquake was the city. Strangely enough, there was surprisingly small damage in the so-called epicentral region. For an 8.1 magnitude, really surprisingly small damage. But enormous damage in Mexico. Nearly 20,000 deaths. But only in a very small part of the city. A very surprising thing. Now let's see what is destruction meant. The picture here from National Geographic says it all. You can see why 20,000 people died. If you recall that the buildings that collapsed, this pancake type of collapse, were typically 10 to 15, 17 stories high. You understand? If a 15-story high falls like this, you understand that the name of the deaths will not be insignificant. It was nearly 20,000 deaths. Now, let's see what's happening in the city. Now, let's start with a very, very crude geological, geotechnical section of the city, which city comprises more or less the area that is shown here on this circle. You can see here the typical dimension of 5 kilometers, and also a very crude sketch of a cross-section through the city. Now, the city contains a hilly zone, a lake zone, very famous lake zone, because it used to be the lake when the Aztecs were there. There was the island, the little island of Tenochtitlan, if I believe was the name of the capital of the Aztecs here. Then this lake was completely dried up when water started being pumped out for the increase in population. And well, this is an area of very soft soil, as we'll see in a while, which soil increases in depth as we move out here. Zone 2 is a transition zone. Now, what is important